The AWS Solutions Architect Associate certification demands deep architectural understanding. It requires moving past surface-level memorization tutorials to understand the physical reality of the hypervisor. A virtual machine in the cloud is an illusion. An EC2 instance is a temporary assembly of three independent vectors: logical network routing, physical hardware placement, and volatile memory state. To see how these vectors interact, we need to strip away the user interface and trace the exact path of the underlying architecture. Engineers often deploy instances assuming they behave exactly like on-premise servers, but cloud abstractions are volatile by design. IP addresses release, physical hosts degrade, and memory wipes on a restart. To build systems that actually survive failure, you have to stop treating servers as monolithic boxes and start orchestrating those underlying vectors independently. Every time you stop and restart an instance, the hypervisor deallocates the underlying host. The public IPv4 address you relied on is immediately released back to the AWS pool, and a completely different IP is assigned on the next boot. To solve this routing volatility, AWS virtualizes the network card itself into an elastic network interface, or ENI. The ENI is a completely independent resource that exists outside the lifecycle of your compute instance. This virtual network card holds your primary and secondary private IPs, your MAC address, and your stateful security groups. While an ENI gives you modular control over networking, it is permanently locked to the specific availability zone where it was created. It cannot cross boundaries into other zones. This constraint still allows for rapid recovery within a zone. If a primary instance suffers a kernel panic or hardware crash, an automated script can detach the ENI from the failing hardware and instantly attach it to a standby instance. Because the MAC address, IPs, and security rules travel with the ENI, the standby node adopts the exact network identity of the crashed instance, immediately routing incoming traffic without waiting for external DNS changes to propagate. Separating the logical network interface from the physical motherboard provides a hypervisor-level failover mechanism that operates in fractions of a second. By default, the AWS hypervisor places your instances onto any available physical blade in a data center. For highly synchronized workloads, this random distribution introduces unacceptable network latency. A cluster placement group forces AWS to pack your instances as close together as possible, typically within the exact same physical server rack. By combining this proximity with the elastic network adapter, you achieve up to 10 gigabits per second of bandwidth with single-digit microsecond latency between nodes. That extreme performance introduces a structural vulnerability. Since every node shares the same rack-level power supply and top-of-rack switch, a single hardware fault will instantly take down your entire calculation cluster. To protect critical infrastructure like primary domain controllers, you use a spread placement group. The hypervisor guarantees every instance in the group runs on distinct physical racks, with independent power and network infrastructure, even across multiple zones. This strict hardware isolation comes at the cost of density. AWS hardcodes a limit for this strategy, restricted to 7 instances per availability zone per group. For massive architectures running hundreds of nodes, like Hadoop or Kafka clusters, the partition strategy divides instances into separate logical groupings that share hardware within their partition, but remain physically isolated from other partitions. The architect dictates the physical topology, calculating the precise trade-off between the low latency speed of rack proximity and the structural safety of hardware isolation. Even with perfect networking and placement, complex applications suffer from initialization delays. When you start an instance from a stopped state, the operating system must cold boot, and your application has to slowly rebuild its internal memory caches. EC2 hibernation allows you to bypass that startup sequence entirely by pausing the instance and preserving the exact internal memory state. Instead of powering down normally, the hypervisor serializes all active data sitting in the volatile RAM and writes it directly into a hidden file on your root network-attached block storage volume. Because active system memory regularly holds plain text passwords, session tokens, and proprietary business logic, AWS mandates a strict internal security prerequisite. The root storage volume must be cryptographically protected using the key management service, ensuring the memory dump is secure at rest. This capability requires the instance to use an approved operating system, have under 150 gigabytes of RAM, and remain in the suspended state for a maximum of 60 days. Upon waking, the hypervisor dumps the saved file back into physical memory. The application resumes executing in a fraction of a second, perfectly preserving both operational state and strict data security. When a hardware blade suffers a catastrophic failure, a standby node on an isolated rack instantly wakes from hibernation, reloading its warm application cache while its network identity seamlessly snaps into place. A recovery sequence this fast and deterministic cannot be achieved if you treat the virtual machine as a permanent object. AWS provides the logical primitives. You dictate if the network interface is portable, if the physical placement is isolated, and if the memory state persists. By orchestrating these three vectors, you build infrastructure that absorbs hardware failure and renders it completely invisible to the end user.